Hello and welcome to this Geometry and Topology seminar. Thank you very much to the organisers for the invitation. It's a lovely idea to get a bit more research collaboration going between different groups of people who possibly struggle to get to other seminars. So my goal today, with the scope of the seminar in mind, is to get you from my research interests to open questions that I think are challenging but are approachable without reading masses and masses of background literature. And we'll see how we go. So the title is Regular Maps and How to Avoid Them, and I'm going to focus on growth and asymptotic dimension, two well-known invariants. So if I figure out, so the type of maps I'm interested in are regular maps, and these are sort of encompass a lot of things that you think about in coarse geometry. So a map between two metric spaces is called kappa regular, for some kappa at least one. If the map is coarse Lipschitz, and we always put on some kind of injectivity condition, and this one is a very, very weak one. So it's somehow some uniformly proper condition. So simply that if you take a pre-image of a ball of radius 1 in Y, you can cover it by kappa balls of radius 1 in X. And the reason I'm interested in these is because there are simply tons of them. It's a huge long list, which I'm not going to read all of. But for coarse geometers, for geometric group theorists, the first three are probably very, very interesting. So these, if you're looking at bounded degree graphs or lots of the things that we sort of interested in related to them, then any quasi-isometries or coarse embeddings between these graphs are also going to be regular maps. So you can think of regular maps as a class of maps that generalize inclusions of finitely generated groups. You've got two finitely generated groups, one's a subgroup of the other, then the inclusion with respect to the word metrics is going to be regular. A second one is the same thing, but for bounded degree graphs. If you have two bounded degree graphs and one is a subgraph of the other, the inclusion will be a regular map. So we like to think of there not being a regular map between two things as some very strong version of the first one is not a subgroup or close to a subgroup of the second, and the first one is not close to a subgraph of the second. The other 4 points are famous examples. The first three probably better known than the fourth. The fourth is a wonderful thing. Assad's embedding theorem for doubling metric spaces. The Bonkschram embedding theorem gets you hyperbolic graphs into real hyperbolic space. And Boyalo-Drunichnikov-Schroeder will get you real hyperbolic space into a product of three regular trees. And I'm particularly interested in these results because they're very, very strong and very, very useful. And so you'd like to know in some sense, in what sense are they optimal? Are they the best types of these types of embedding we could have? And so that's sort of where my interest in regular maps lies. Okay, so those are regular maps. There are tons of them. We've hopefully established a motivation for wanting to obstruct regular maps. And now what I'm going to do is try and explain to you what the tools are, traditional tools that we had for obstructing regular maps. The first one hopefully is well known, it's the growth function. So my little disclaimer, I'm going to talk about bounded degree graphs for the remainder of the talk. If the things you're interested in are not bounded degree graphs, then we're all happy as long as they're quasi-isometric to some bounded degree graph, because all the invariants that I consider, you could just pass to one of these and it doesn't matter which one you chose. Just makes growth a little easier to define. Okay, so the growth function of a graph, what do I do? I'm going to take sort of an upper control on the growth function. So I take the maximum over all the vertices, and then at each point I'm going to count the number of vertices I can get to within a path of length n. Okay, and as is typical, but maybe worth writing down once if you haven't seen it before, a refresher. The exact growth function is not going to be a QI invariant or well-behaved under regular maps, but more the kind of asymptotic growth of it is going to be well-behaved. So we consider growth functions and on most other functions in this talk up to this equivalence relation listed here, where we say f is sort of roughly at most g if it's sort of asymptotically controlled, right? So this is f of n is at most cg, cn plus c, all these kinds of things. And to give you just a quick example, when I find the annotation thing, this means that n to the a is at most n to the b for a at most b, but say 2 to the n is equivalent to 3 to the n is equivalent to 150 to the n. Okay, so this will be an if and only if condition here. So we can tell apart different types of polynomial growth, but exponential functions all go into one class. And the important thing for our purposes is if you've got a regular map between two bounded degree graphs, then the growth of the first one is at most the growth of the second. So simply counting points, if there are so many points in a ball of radius n in x, there must be a comparable number of points in the ball of radius kappa n plus kappa in y. And we know quite a lot about the growth function. This makes it very useful. It's particularly for finely generated groups, we know a lot about the growth function. So when you're trying to deal with invariance and you have a new invariant to play with on a class of groups or a class of graphs, you would like to know, well, which things, according to this invariant, are small, which things are big. Okay, so small in the case of growth is usually considered to be polynomial, so the growth function being equivalent to some polynomial. And of course, we have the famous result, Gromov's polynomial growth theorem, that a finely generated group has at most polynomial growth if and only if it's virtually nilpotent. So we really understand the sort of small case in this situation. There's also a large case exponential growth, and in some sense, most groups you meet, unless you happen to be very interested in nilpotent groups, lots of groups you meet from topology, lots of groups you meet from knot theory, all sorts of things like this, have exponential growth. So non-amenable groups, any elementary amenable groups that are not virtually nilpotent, they will have exponential growth. And then I didn't realize my annotations were going to stick around. Maybe I'll go to delete them at some point. And then intermediate growth, it's another fascinating class of things that are going on. So for intermediate growth, we have the famous first example being Grigorchuk's group acting on a rooted tree. And of course, for plenty more examples. And as far as I'm aware, there are no finally presented examples yet. And I'm not suggesting with this slide that there's nothing more interesting to say about growth. A particularly nice conjecture is Grigorchuk's gap conjecture, which says that the growth function of a finely generated group is either polynomial or at least, if I remember correctly, exponential of the square root of n. I don't know what the situation is on that. I think it's very, very far from being resolved. I'm still trying to erase things. The second invariant is asymptotic dimension. So this is introduced by Gromov in the huge asymptotic invariance tome. And here I will recall the definition for you a bit more clearly. So we say X has asymptotic dimension at most n if for every r we can break X up, we can color it using n+1 colors. So this is this superscript indices 0 to n. So we say for each point it has a particular color from 0 to n. And then we take each color and we're going to break each color section up into a large collection of pieces. And the important thing about these pieces are these two conditions here. The first is that they should be any pair of them, so those the same color, but different blocks of that same color should be at least r apart. And the second condition is that all these pieces in our decomposition should have uniformly bounded diameter. So you can think about this, might find a convenient way of thinking about this is that this is a graph coloring problem, but on a large scale. So we're thinking of a vertex coloring. Instead of coloring vertices, we're coloring regions. Those regions have to have bounded diameter, so they're sort of vertices, or sort of uniform thickenings of vertices. And instead of saying that adjacent vertices can't be the same color, we say blocks that are close enough cannot be the same color. Okay, so that's the definition for asymptotic dimension at most n. And for the equality, we say you have equality if asymptotic dimension is at most n, but asymptotic dimension is not at most n-1. So like growth, the key property that we're interested in for this invariant is its behavior with respect to regular maps. And here it's nice and straightforward. If there's a regular map from x to y, then the asymptotic dimension of x is at most the asymptotic dimension of y. As with growth, asymptotic dimension you can think of as splitting the world up into things that asymptotic dimension thinks are small and things asymptotic dimension think are big. Okay, and so of course there's the spaces that have finite asymptotic dimension. So first I'm going to give you here real hyperbolic space of dimension k, Euclidean space of dimension k, and a product of k, 3 regular trees. These all have asymptotic dimension k. Other things that we know have finite asymptotic dimension, polycyclic groups, and in fact we even know you can, once you write down the polycyclic series, you can just read off the asymptotic dimension as the number of infinite cyclic factors in your decomposition. Hyperbolic groups, we have an upper bound due to rho, which is far too big in general. It's not going to be the optimal thing. And then we have a much better understanding because it's equal to the topological dimension of the boundary plus 1. And there are some tools for calculating that. So have a reasonable understanding there, but not perhaps complete. Right angle arctan groups, it's one minus it's the cardinality of the largest clique. Sorry, it's exactly the cardinality of the largest clique. So just the fact that it's got a free abelian subgroup of a particular rank. Mapping class groups, so we know it grows at least linearly in the genus of the surface because you get free abelian groups of that size, and it grows at most quadratically in the genus by work of Bear-Stock, Hagen, and Sisto. That's the best bound that's known so far, and they extended this to all hierarchically hyperbolic groups. So large classes of groups for which we know the asymptotic dimension is finite. For infinites, the possibly an easy example is the Reed product of 2 copies of the integers. So that has z to the n as a subgroup for every n. So that gives you a lower bound of n for every n. So that's an infinite asymptotic dimension space. Thomson's group also has z to the n as a subgroup for every n. Grigorchuk's group doesn't, but the way that these constructions of groups of intermediate growth typically work is you show that the group is commensurable to a direct product of 2 copies of itself. And so you'd have a quasi-isometry between G and G times G. So if it had finite dimension, you would have space of dimension K is comparable to a space of dimension strictly bigger than K. So this gives you, although it doesn't give you Z to the K, it gives you QI embedded copies of Z to the K, even though they aren't there as subgroups. And as far as I'm aware, all known examples of intermediate growth groups rely on this in some way. And so there's no example where we could try to have a hope of proving that they had finite asymptotic dimension. Please, corrections if I'm wrong. And well, we don't have an intermediate. It's either finite or it's infinite, but there's plenty interesting enough class of spaces where it's unknown. And the big headline one is always out Fn. But we also don't know in general for arctan groups whether all arctan groups have finite asymptotic dimension. And we don't understand really, as I pointed out, the asymptotics of the asymptotic dimension of the mapping class group. Okay, between linear and quadratic in G, but which one is it, if it's either of them? And so now I want to get onto a new toy. So this is the new toy I'm going to talk about today, and the thing where, even compared to the last 2 things, almost nothing is known. So hopefully there's plenty of scope for new projects for people to get interested without having to read hundreds of pages of background literature. What I'm going to do is I'm just going to bolt the 2 definitions together, asymptotic dimension and growth. So pick a collection of functions, f. Okay, these are going to be growth functions, or sort of equivalence classes of growth functions. And we say that x has asymptotic dimension at most n modulo f growth. Someone should be in charge of naming, and I don't think it should be me. Okay, we'll just write this as an asymptotic dimension. That subscript f should probably be before the x, but never mind. So the asymptotic dimension with respect to f of x is at most n. If we can do the same decomposition, so again, there are going to be n plus 1 colors. Each colored region is going to be split into a larger collection of pieces. They're still going to have to be r apart. But now what I'm going to ask is, instead of having bounded diameter, I just want to uniformly control the growth. Okay, so just give me some uniform control on the growth, or equivalently the growth of, so the disjoint union, treat it that way. Okay, so this growth is bounded in this partial order by f for some f in class capital F. Okay, and so this gives us a lot of freedom to choose the capital F as we like for whatever situation we're in. And we say the same thing. The asymptotic dimension is n if it's at most n, but not at most n minus 1. And like the other two cases, we have this invariance with respect to regular maps. So if you've got a regular map, then for any f, you can pick whatever f it is that happens to suit your purposes. The asymptotic dimension of x with these f pieces, these f's are wandering around all over the place. This is probably the correct way of, probably a more sensible way of writing it. So we'll try and, hopefully I've stuck with that one at least for a bit. Okay, then for every f, for every collection of functions you might care about, the asymptotic dimension of x with respect to f is at most the asymptotic dimension of y with respect to f. So if you just want to tell two spaces apart, maybe you can pick the right collection of growth functions and do it that way. So we'll have the optimistically titled slide, What Do We Know? Well, one simple thing we can start with is, if we just take a collection of constant functions, then for graphs at least, bounded growth and bounded diameter are the same thing. Okay, so the asymptotic dimension with respect to f is exactly the same as the usual asymptotic dimension. So we've got a collection of invariants that just extend. What's going on here? Another one is that if the growth of x itself is in f, then the asymptotic dimension with respect to f is 0. Now, I'm going to tell you all I know about it, which amounts to one interesting way of finding lower bounds and one interesting upper bound. And then I will throw you a lot of open questions, and the rest is up to you. We can chat at coffee or work it out another way. So we have one interesting method for finding lower bounds, and it concerns distorted subsets. So this is going to be for a very specific class of functions f, which is the class of functions that grows sub-exponentially. There are other versions available for polynomially growing things. We could talk about that if that was something that interested people. So if you've got an inclusion of graphs and an epsilon positive such that this equation holds, what does that mean? Well, the way we'd more normally write it is by taking logarithms and doing things the other way around. We'd say that y is exponentially distorted in x. Okay, so examples of this are a Horner cycle in a real hyperbolic space. Okay, so if we have an inclusion, like an inclusion of a Horner sphere into a hyperbolic space, and the dimension of the thing we're embedding is k, then we'll get the same lower bound for the asymptotic dimension of x with respect to the class of sub-exponentially growing functions. Right, so if you try to say, well, I'm going to cover it, but I'm only going to use functions that grow sub-exponentially, okay, then this is going to give you a lower bound. And as a corollary, well, it's the one I've mentioned to you. So you try to cover real hyperbolic space, and you say, well, obviously, if I tried to cover it with something exponential growth, I could just put it all in one pot, and that's dimension 0. So the first interesting thing is to say, well, at least I'll limit myself to the class of sub-exponentially growing functions, and already something interesting happens. Okay, so if you try to cover real hyperbolic space by that, then it has dimension k-1, so it needs at least k colors. So that lower bound is 1 lower than the usual asymptotic dimension, and that's apparently all the gap you have to play with between bounded diameter and sub-exponentially growing pieces. Okay, less obvious, so using a little bit of an adaptation of this method, what I've told you, the result I've told you about doesn't work exactly, but some variant of it does. You can show that a direct product of n trees, which has asymptotic dimension n, also has asymptotic dimension n with sub-exponentially growing pieces. And this sort of sounds intuitive. You're trying to break down a product of exponentially growing things using sub-exponentially growing things, it just doesn't feel like it should work. It should offer you any advantage, and that indeed is the case. Okay, so these are kind of big things in this for this dimension. So that's lower bounds. We can do something like this, and I know precisely one interesting upper bound, and it's for the hyperbolic plane. So I'm going to try and do, we'll see how this goes, is I'm going to draw you a picture. Okay, so what I'm going to do is I'm going to take a quadrant of the upper half space model in the hyperbolic plane, and I'm going to take along this positive imaginary axis a collection of equally spaced points with respect to the hyperbolic metric. So that's a collection that's growing exponentially as we are looking at it. So something like this, maybe. So a couple more. Okay, and I'm going to now build a comb. So I'm going to extend from each of these points a geodesic that's orthogonal to this positive imaginary axis. So that gives me a selection of quarter circles. Promise, attempting to draw quarter circles. Don't promise that I'm succeeding. This takes far more concentration than giving the talk. Hey, that's actually not too bad. Okay, and that would carry on. Okay, so this is my starting point. And what I'd like to point out to you is that this comb, so that's this line down here with all these things coming off it, this has quadratic growth. In fact, it looks like a comb. So it looks like a copy of the integers where at each point I put on a line for the natural numbers, right? And so it's that graph where you're just allowed to go, it's that tree where you're allowed to go, okay? Why does that work? Well, we're in a hyperbolic space and these geodesics are diverging. So they stay close for a very limited period of time and then they're traveling off at a linear rate. So if we look at this comb thing, this thing is quadratic growth. Okay, so now if we've hopefully figured that bit out, I'm now going to draw you a picture. So I'm going to start with this, again, with this vertical ray, and I'm going to take an R neighborhood of it. So that is a wedge, something like this. And this is the capital R neighborhood of this vertical strip. And then I'll take another R neighborhood of that, thing like this. Okay, so that's the R to 2R annulus around it. Right, and so that's going to be the first two pieces, and I'm going to give you another piece to do. So what I'm going to do is I'm going to connect up all of these guys along the bottom line by semicircles, by infinite geodesic semicircle, look like semicircles in this model. And what I'm going to tell you is that using hyperbolic geometry, so this semicircle here, although it doesn't look like it on my picture, is within a uniformly bounded distance of the rest of this quadrangle. Okay, so this is a by infinite geodesic. This is a geodesic ray, and a finite geodesic of uniformly bounded size. So just by hyperbolicity, these three sides are uniformly close to this side. What does that mean? That means that if when I take my next red thing, I look at a little r, I thicken each of these by r. And I take all of this region to be one thing. This thing has so same growth as the comb, i.e. it's quadratic. Okay, so all of this is included in that red region. And that single red region has quadratic growth. And then what I do in each of these semicircles is repeat the picture. So this was an R neighborhood of this geodesic. So I then take another R neighborhood in blue. And then I do the same cone type thing in red. And repeat. Now, because this blue region is an R to 2R annulus, the distance between any pair of red things is at least R. And because in each of these regions I take another R neighborhood of this black curve, the distance between any two blue things is greater than R. Okay, so this horrible mess is a proof that I can color the hyperbolic plane using two colors, keeping pieces of the same color at least, any capital R apart, where the red pieces have at most quadratic growth and the blue pieces have linear growth. End of my messy picture. Oh, that wasn't very clever, Jason. Okay, so as a corollary of this, thought I was going to turn up on a different slide. As a corollary of this, that's clearly my picture. As a corollary of this, I can do the same thing for higher dimensional real hyperbolic spaces, although I definitely can't draw you a good picture of them. Okay, and so this relies on what you do is you say, well, there's a map from hyperbolic K space to K minus 1 copies of the hyperbolic plane. And in the upper half space model, it takes x1 to xn, K minus 1, xk. So these being the Euclidean, the real coordinates, and this the imaginary one. And you take it to x1, xk, x2, xk, and so on. Okay, so up to xk minus 1, xk. So that's a nice bi-Lipschitz embedding. And you, in a sense, you find a product cover over here using Kolmogorov trick, and you pull it back. And this will give you this upper band. Okay, so the second corollary of that is that, say, asymptotic dimension R to the K of hyperbolic K space, that's equal to the asymptotic dimension where you allow any sub-exponentially growing pieces, and it's equal to K minus 1. Okay, so if you allow exponentially growing pieces, you get 0. Sub-exponential, you get K minus 1. All the way down to R to the K, you'll still get K minus 1. So now I can give you open questions. I thought annotations were going to disappear between slides, but they're not. Okay, so open questions. My first one concerns precisely this. So let's not delete it instantly. What happens if I pick smaller growth than R to the K? What if I pick R to the A for some smaller power? Will I go up to full dimension straight away? What happens? That's my first question. So is this construction that I've made and given to you really the best thing? And then you can just start acting for whatever class of groups you're interested in. So I know what happens for tree times tree. I'm going to get dimension 2. What about surface group times surface group? Hyperbolic surface group. So Euclidean or Z squared you could put in there. What things do we get there? What in general do we get for free products? We don't have a good result for free products. Similarly, direct products, you could start with a direct product of 2 surface groups and try and figure out what was going on there. Another thing that, well, possibly even more naively, we might like to know what happens for Euclidean space when we allow the polynomial growth degree of the pieces to get bigger and bigger. Okay, so if you allow bounded growth, you're going to get the usual asymptotic dimension. And if you allow pieces that grow like R to the K, you're going to get asymptotic dimension 0. And so do you just step up 1 each time you see a new integer? Seems like naively you would hope that the answer was yes, but it needs to be proved. There's going to be some new idea needed to actually do that. And then I think even more interestingly, assuming you're able to do that, is how you might push this thing onto nilpotent groups. So if you've got G finitely generated nilpotent, you've got the lower central series, so C1 of G is G and C, K plus 1 of G is the commensurator of G with CK of G. These common quotients, CK over CK plus 1, are finitely generated abelian. And so we can say the rank of the free abelian factor, we'll call that NK. So what we know is the asymptotic dimension of G is the sum, and they're not called MKs, they're called Ds, I think. Let's call it D. dk. So the asymptotic dimension is just the number of free abelian factors. That's the sum of the dk. The growth of the G is n to the d, where d is the sum of these things, but normalized. So if we look at asymptotic dimension with r to the k of G, this is going to be, well, sum of the dk too many k's. So I do growth r to the m. There's going to be sum of the dk for m equals 0. I mean, it's some other values, and then it will be 0 for m equals some k times dk, and it will be at least 1 the step before that. Okay, so we're going to get some non-increasing sequence of integers starting at the asymptotic dimension and going to 0. There's far more steps here, right, than there is. So it doesn't go down 1 each time. That's probably what happens if it's the free abelian group. So it'd be interesting to know, when does it change? So what steps do you actually see a new thing? Right, and I'm going to finish with that question. Or I might have put some questions about regular maps. I did put some questions about regular maps. Let's erase the thing. We can look at those. So I left with 2 questions about regular maps that I don't know the answer to, where I also don't think necessarily these invariants are going to help me too much. So if you go back to some of the embeddings we've talked about today, then there is a regular map from hyperbolic 3 space to a product of 3 regular trees. So is that essential? Is the 3 regular tree the only thing you can put in that last space? What about if you put a Euclidean space? Can you do it? And you can also embed into hyperbolic 3 space either into a product of 2 hyperbolic planes. So what about swapping a hyperbolic plane for a tree times r to the n? Does that work? Right, I'll leave it there before I keep coughing on you. Thank you very much for your attention.